In an earlier video, we have seen the convolutional neural networks and the basic operation. In this video, what we're actually introducing here is residual networks, which is to this day, several years after their introduction, remain one of the main used architectures for feature extraction, and not only, as a basic component of many more advanced CNN architectures and that are doing more complicated tasks, such as object detection, semantic segmentation, and others that we will see in another video. So the history, if you like, of their introduction, started around 2015, where people realized that it's not really possible to extend the so-called architectures of the time, let's say the VGG architecture. We've seen the VGG architecture on a different video earlier in this actual topic over here, where we have seen the sort of architecture of the VGG16 network. And what was actually happening then, and now that we understand a couple of things about backpropagation, the gradient had a lot of problems to flow all the way to the input of the network, and the sort of bottlenecks that were actually generated created significant problems in the training of these architectures. So around 2015, a researcher at Microsoft found a solution on how to enable that gradient to flow freely in much deeper architectures, such as the ones that we will see in a moment. And this gave the name Residual, because in that architecture we implement what we call a residual unit, and from now on we'll refer to those networks as ResNets. All right, so in order for us to understand what is going on with ResNets, so what I'm going to do now is I'm going to draw a very small ResNet architecture, just consisting of 3 units. And if I may draw the architecture, that's my unit, which I'll abstract with letter F1. So the input to so I'll use a bit different terminology from what I was used kind of earlier. So I'll be calling, instead of X, I'll be calling it Y0. I could have used it also X0, but in my notes over here I have this as Y0. Okay, so the Y0 goes into a block that will consist of one or more convolutional kind of layers. And in the residual architecture, and this is why we call it residuals, we take the input and add it with a unit gain into the output, Okay, so to form what we call now a Y1. The Y1 is being added into, again, with exactly the same approach. And this is the output, Y2. And the Y2 is similarly added to form the final Y3 output. Okay, so this is the kind of a basic ResNet kind of architecture and if you compare what we have seen earlier with the CNNs, we had convolutional layers, max pool layers, and so on, nonlinearity evidently over here, but we never had this kind of skip over connection, as we call it. Okay, so I want to just go ahead and write now the expression of the output of each of these blocks with respect to the input. So I hope you agree that this is exactly what each of these blocks is implementing. Okay, so we have the fi of yi minus 1 plus the yi minus 1 in each of these. So if I may write down these equations for, let's say, the y3 is equal to f3 of y2 plus y2. The y2 itself is f2 of y1 plus y1, and the y1 is f1 of y0 plus y0. These are the three equations for each of the three blocks that I have here. And what I want to do now is I want to start replacing the y2 and the y1 into the equation y3, because I want to write down the equation, the form of the y3 as a function of only the y0 and the two functions that are involved in the blocks f1 and f2. Okay, so all right, so what I'm going to do now is I'm going to write it as f3 of y2, I'm sorry, f3 of f2 of y1 plus y1 plus f2 of y1 plus y1. Okay, so I just replaced the y2 with its equal, and now I can replace now let me write it over here because I just need a long line to replace it, to make the final replacement. So it is f3 of f2. Now I'm going to replace the y1 with its equal to obtain the final expression. And this is now the second square bracket. Okay, so it is really this bracket over here, plus I have f2 of f1 of y0 plus y0 plus f1 of y0 plus y0. Okay, so this is my final expression with respect to the output of y3. And why I did that, I want to take this kind of architecture and write its equivalent that were just based on this equation. And that kind of plotting or drawing of this kind of architecture will help me kind of understand a couple of things about the advantages of ResNets and why they solve the problem of gradient flow throughout the network. Okay, so I am going to start. So I'm dividing this into two parts. I am going to first draw the long part over here, this f3 expression here at the bottom. So I am going to take this accepts as input y0. That's the only input in this diagram. So y0 is going into the function f1. We are adding now the function, the y0 into it. Okay, so that's basically this term. All right, so then we take the f2 of this term. So the output of this is being fed to f2. And what we do is we add, for this f2, we add this term over here, f1 y0 plus y0. So we add to it another block involving the function f1. Okay, so this is basically this inner term over here, and then finally we are taking the f3 of that. So this is basically my F3. So if I am a circle, if I may circle this, this will be, let's say, A. This A will be available over here. Okay, so we have now finished with the plotting of the first term. And now let's look at the second term. So the second term is simply F2 of y1, y0 plus y0. So I am going to go again here. This is in fact just one line. So I'm going to just take again F1 of y0 plus y0. And I'm simply going to take the F2 of that. And this thing over here is the point B. However, so this is basically B. Let me draw it over here. To B now, what we have is we simply add another of these guys. We add to B this, and I would like to circle that over because we see here three things being involved, A, B, and C. So this is C. And then B and C are added to A. And this will actually be my Y3. And now that we have this kind of diagram, we actually can make some really nice conclusions out of it. As you can see, the gradient in the backward pass. So the point number one I want to mention is about the gradient flow. So you can see the gradient flow in the backward pass during backpropagation now has a diverse set of paths and to actually flow all the way to the input. Let's say it has this path that simply just follows all the way to the input y0, the other path that goes through this F1 to go to the input, this path through F2 and the concatenation F2 and F1, or via this skip connection to go to F0, and so on and so on. So what we see here is we have a diverse set of paths through each goes through sort of gates, I will call it, because this is what we have used as a term in backpropagation of varying depth. Okay, for varying depth. So that's kind of important. Earlier, what we had without those kind of skip connections, we had simply F1 concatenated with F2 concatenated with F3 in the so-called, let's say, VGG architecture. So here we had a backpropagation that it was involving just a single trajectory, a single path through all of these gates. And at some point, the gradient was actually dying. And of course, a dying gradient means that the specific functionality of my network, they are being updated, the parameters are being updated very, very slowly, or just simply cease to be updated. So that's not really, I mean, this is one of the key observations that led to some kind of a leveling of the performance of these earlier kind of architectures as the number of layers were being added up. In this kind of architecture, we are effectively implement what is actually known as highway networks, and those highways that we're creating for the gradient empirically has shown that we actually can go much deeper. So we'll see now some depths, typical depths that we experience in we have in ResNet architectures in a moment. The second aspect of that is a bit more nuanced, and it has to do with what we call an ensemble learning. So in this kind of ensemble learning architecture, what we see is the concatenation, the combination of three predictors here, three main prediction architectures. Each of those predictors has a varying kind of functionality. So we see a fairly involved predictor, which we call A. We see another predictor which we call B, and another predictor that we call C. And what we see at the output are the kind of combination of those. Simply, if you are familiar with ensemble kind of methods, which I'll provide some kind of background in a moment, we are adding the individual prediction results given the input y0 to obtain our final prediction output, the so-called y3 hat. Okay, and so that's ensemble methods have proven in the field to be a very powerful approach in solving complex kind of tasks. And in fact, ensemble methods are being used both for structured and unstructured data. And in the structured kind of data field, you have methods such as gradient boosting and so on, providing some really state-of-the-art results today. So a few words about ensemble methods is arguably a parenthesis, but I think it's a kind of worthwhile sort of discussing a little bit about ensemble methods. So there are various ensemble methods, but I think a common denominator for many of them is that the prediction y hat that we get from the so-called ensemble, also known as committee methods, where we form a committee, a group of experts or weak learners, as we call them, let me call it y hat committee, is simply the average, let me call it 1 over capital K, of the summation from small letter k is equal to 1 to capital K, where capital K is the number of predictors that we have here. We had 3 in the ResNet architecture of y hat sub k. So the premise of ensemble methods is that we don't necessarily need to have the single silver bullet that will solve the very complicated kind of task of us that we have in front of us, but a number of what we call the so-called weak predictors that it will not perform individually very well, but on aggregate they will actually perform much better. And that is really the premise of that. And one parallel architecture we have in the earlier method that we call the ResNet is kind of resembles that kind of architecture, because we have some kind of a summation combination of these weak predictions, the so-called A, B's, and C's that I have explained earlier. So the in ensemble methods in general, we can consider performance-wise to consist of in somewhere in between 2 bounds. So the lower bound, the so-called lower performance bound, is obtained evidently when you have very correlated predictions. And if you are not able to randomize the operation of each of these predictors somehow, we are going to exhibit this kind of lower bound where either you form a committee or not, you get exactly the same performance. It's just like the analogy or the equivalent analogy I would like to sort of share is you have a committee of, let's say, a human committee of human experts, but each expert went to exactly the same school, studied exactly the same field, had exactly the same university professors, and they are actually now called to solve the problem. And guess what? Each one of them is actually offering exactly the same view. Well, that's basically where the point where you're experiencing a lower performance bound. And the upper performance bound is a bit more nuance, a bit more complicated to kind of understand, but the best performance what we can actually get, I think it's better understood with an analogy. You don't expect every committee member to not make mistakes. They will make mistakes, but what you want to do is to have a committee that they don't make the same mistake at the same time. So the so-called uncorrelated errors are involved in sort of showing some kind of a performance bound that is kind of outside of the scope of this course. But I think it's worthwhile providing some kind of guidance as to where and how we will be able to achieve that upper bound. So the main three ways that we can achieve this kind of upper bound or try to achieve the best possible performance out of ensemble methods. The first is the data component. Can we provide in some way different data to to the various kind of weak predictors that we have here, so that we do not cause exactly the same conclusion for each one of them. So the second is to somehow randomize their operation. So randomization is the second kind of approach there. And I can offer an example of randomization. Maybe we can actually offer a different set of hyperparameters sort of picked by some kind of distribution in this architecture you see over here in this course. In some other approaches where we have, let's say, decision trees involved in these predictors, again for structured data I'm referring to, then we can randomize their operation by picking different features that they split their sort of trees. And there are so many approaches that are, I guess too many to quote over here. But the third approach, which is a bit more relevant in this specific ResNet architecture, is to simply use different predictors. Or weak learners. So the weak learners that we called over here are involved in the ResNet architecture. And so here we have a predictor of some complexity. We have here another predictor of a larger complexity, and yet another predictor or even larger complexity. We have effectively implementing the third approach, where we have those different weak learners. Each one is offering a view, and then finally the network is deciding based on the composition of those views. Okay, so that has been shown to sort of provide performance advantages, and that's what we kind of had this discussion about ensemble methods. And the third kind of advantage I wanted to quote here for ResNets is their scalability. So the scalability should be understood from the point of view of complexity. We are effectively able to have 3, 6, 9, or whatever number of residual blocks. Each one of them will actually be exactly the same as any other block over here, and therefore we are able to accommodate architectures that have various number of these blocks. Let's say we see ResNets with 18 layers, 34 layers, 50 layers, 150, 102 layers, even 150 layers. These are the numbers that we have defined already existing architectures. And this is kind of important when you have perception systems that need to comply to some real-time latency requirement. Evidently, the larger the number of layers you have, the longer the latencies that you are going to experience taking an image through this kind of pipeline. So if we have, let's say, a latency of, let's say, 80 milliseconds, we can, and therefore we are not able to accommodate 102 layers. We're definitely going to be accommodating, let's say, 50 layers. And the exactly the same technology, exactly the same thinking and behavior of ResNets will be in either of the numbers quoted here in terms of number of layers. So all of these three advantages are coming together to provide a fairly robust architecture, has actually proven in the field in both real-time and non-real-time applications, and able to extract features, provide, if you like, representations on visual imagery that we have, the imageries that we are feeding into them.